So essentially, we're going to start with the basic SEIR slides. It's a surface method, done from the top surface. Sonic echo is time domain analysis, which is what we're doing here. Impulse response does the same, uses the similar data with an instrument hammer and does a frequency domain analysis. So we'll show that quick, but we won't talk about it too much. Okay. And so you're impacting the top of a foundation, looking for echoes. That much you know, certainly. There is an ASTM standard. The 07 is now, should be updated, but it's D5882 is the ASTM standard for SE testing. We've used it on drilled shafts, auger cast piles, driven piles, sometimes wall structures we've done it on. Mat foundations, big, thick mat foundations, 10, 12 feet thick, big, large blocks of concrete in the ground. We've done echo testing on that, and it can work as well. It works best on drill shaft foundations, and the shorter and fatter, the better it works. Okay. Shorter and fat. The limitation, I don't know if we're going to talk too much. I think we have some of it in here later, but this is the basic method, what you're looking at. So you hit on the top, you got a receiver. On a normal shaft, it goes to the bottom, comes back up to the top. If you have a neck, it will echo early. The relative size of that neck will depend on the relative strength of this echo versus this echo. So if you have a neck that's 20% of the cross-sectional area, that's considered barely visible. Okay. If you see a neck, if you can see it clearly, it's probably 20% or more. Okay. The cross-sectional area, based on research that we've done over the years with FHWA and other folks, where they put known defects in the shafts at different depths, and typically it had to be about 20% of the area. Different people sometimes say 15, 25, but in that range of the cross-sectional area to be visible at all. Once it's 100%, of course, you'll only see the break. So those are the two extremes. Is 20%, you'll barely see this echo, and you'll still see a pretty decent echo from the bottom, ideally. A full break, you'll only see this echo with no echo from the bottom. At about 50%, they might be close to the same. A lot of it depends on how long and skinny your shaft is. But so essentially, the larger your neck, your shallow echo is, the bigger it is compared to the bottom echo. And at some point around 50 to 60%, the bottom echo disappears completely, and all you see is the shallow echo, in my experience.
Did this breaks or crack that include cold joints?
If it's unbonded cold joint.
Okay.
A cold joint isn't necessarily a defect.
Right.
As long, and that, because that happens a lot, but cold joints and shafts, it's really hard in my experience to make a bonded, good, clean cold joint in a shaft. Because you have to really clean it out well. The top of the concrete can't be contaminated. And then when you place more concrete on top, you can do that. You can go in there and chip out the top, because depending on how the shaft is placed, if it's placed in what we call the wet with a tremie, first of all, if it's placed under slurry fluid, then you're almost certainly going to create a sand lens if you stop placing the concrete and then try to start up again. Because I don't know, are you familiar with slurry fluid?
Yes. Okay.
So the slurry fluid has all this sand floating in it and other contaminants. And you start placing the concrete in your tremie from the bottom, and it pushes up, and it pushes the slurry fluid up. But the top of concrete, at the interface between the fluid and the concrete, is contaminated. Right. It always is. And ideally, when you're done, it spills out the top, and you clean it up. If your pump breaks or something happens with your tremming, or you run out of concrete, a truck is late, and you have to stop, then your concrete sits there and starts setting up. But that top 6 inches or so is contaminated, mixed in with sand and gravel, and the sand and the slurry fluid starts to settle down on top of the concrete. If you then start to place concrete again, or if you burp the tremie, that's another thing. If the tremie comes up out of the concrete, so it starts placing concrete down onto the shaft instead of up from below, then you've trapped that layer of bad material. Really common defect in a shaft for drillers that don't know what they're doing with slurry fluid.
Right.
You know, if you ever have to pull the tremie out, you're almost screwed, almost always. It's really hard to make a sound shaft at that point. And even in the dry, you know, if you place the concrete, you know, falling it into a hole and it stops and sets up, you have to make sure that top of concrete is really clean if you start placing again. You can get away with it in that case, if it's dry and clean. You know, if the hole dirt doesn't fall down on top, and you know, if you stop it halfway up and then start placing concrete again, you know, make a true cold joint where the concrete sets up, and then you start placing more concrete. So that case, a cold joint might not show up because it'll be bonded and it'll be solid concrete. You know, if it's a dry shaft where you're placing concrete, you stop, then you start up again. But you're dumping the concrete from the top anyways. You're not trying to tremie it up from below. So these are obviously the simplest cases. This is what you're looking for in the shaft itself, a break. And a bulb is a diameter increase or an impedance increase. It's really an impedance increase because the test is really looking at what they call acoustic impedance. So it's stiffness. So a neck is a low impedance and a bulb is a high impedance, or a bottom is a low impedance, so it echoes up, it echoes a certain way. And we'll show you some examples, but you can tell a bulb from a neck based on the polarity of the echo. So what you need basically, top ideally is accessible, or some portion of the upper side. We tell people the top of the shaft or the upper side of the shaft. You can't test a shaft under a grade beam, through the grade beam typically. We've gotten away with it occasionally if the beam is the same width as the shaft and if the shaft's a really large diameter, you can sometimes get away with testing through it. But usually I like to have access to the shaft itself. Right. It's always the cleanest. Top should be relatively smooth. I haven't had to grind a shaft in a long time, but occasionally if they've jackhammered it, it's so rough that you just can't mount anywhere. Yeah. You might need to hit it with an angle grinder or something.
Yeah, that's what we have in our
okay, great. Yeah. So this is testing from the upper side. We've done it on timber piles, concrete foundations. Short steel H piles have been tested successfully, but really short ones. It just doesn't work well on H piles. Okay. The energy, there's not enough cross-sectional area to carry the wave energy. It all dissipates into the soil from the sides of the H pile, because there's not enough meat in the pile to carry the wave energy down. So it dissipates, and by the time it echoes from the bottom and comes back up, you know, the echo is, it's just too small, and it just disappears. So these are the basic systems we use. The data PC, signal analyzer, we have an ND DAC that's our newest piece of hardware that Stan will show you in the back. Okay. ND360, that's replacing the ND360 primarily. 3-pound hammer. By the way, this 3-pound hammer, that's kind of normal equipment for normal shafts. When you get into shorter shafts, anything less than, if it's 15 feet or less, I would recommend using maybe a ball peen hammer. So if you think you're going to be testing some short shafts, I think it's a good idea to have like a 1-pound ball peen hammer in your kit anyways. Okay. You know, steel ball peen hammer. Because if you think you have shallow echoes, the ball peen hammer can make them really come out well. Or if you think that you have a shorter shaft, it can show up really nicely. And I'll show you that. What we have to demonstrate the method is a 10-foot log in the background.
Yes,
that's a short shaft. Okay. It's also a very, very fast log. So
we have the FTG.
Yeah, you have the FTG one, right?
And so I think that they were telling me that anything less than 6 foot on that we won't.
It gets really hard. Yeah, 6 foot is kind of at that point we switch over to impact echo, which is this, you know, it's a frequency domain using a little 1/2-pound hammer or a 4-ounce hammer. You know, it's not that you can't do it, it just won't work very well. Okay. You know, I could show you, we have a 3-foot shaft and we have a 3-foot cylinder in the back room. And we can show you doing an FTG test on a 3-foot cylinder, and it'll look like, you know,
okay.
a lot, but you'll see the echoes will be 3 feet apart. You know, you'll get them. It's just not, so it's not a hard and fast limit at 6 feet. It's just not, it's not designed for that.
Okay.
You know, and you definitely, the 3-pound hammer will not work at 3 feet.
Okay.
You need something like a half-pound hammer. You
But
know,
it's, I mean, if I get a half pound
a ball peen hammer.
or
Yeah.
ball peen, I can still use this.
Yeah, you can still use the FTG and the accelerometer, but your echoes will look very close together. And I'll show you in the back
Okay.
on the log. Yeah. So, and then some data analysis software. These are the systems, the ND360. This is what you have right here, effectively. Some version of that, of a laptop, an FTG, and yeah, accelerometer. And you don't worry about this. This is for the IR testing that uses this is like a $1,400 hammer
Wow.
instead of the cheap hammer. It has a load cell built in here that measures the strength of your impact.
Okay.
So, and the waveform. So it gives a waveform from the impact that we can then divide by the output to come up with the impulse response. So it's an input divided by output kind of thing. So we're not too worried about that. This is pretty straightforward, accelerometer, you connect it up. So this was some grinding done on a shaft. This was a test shaft that the FHWA did 25 years ago or something
Okay.
out in Texas. This particular one, it has extensiometers tubes, it has cross-ultrasonic logging tubes, it has SEIR tests, you know, there's defects in it.
Okay.
You know, so there's an accelerometer here, I think there's maybe 2 accelerometers, there's a geophone, an impulse hammer. So, typical test that's set up though. Now, one thing they like, based on the ASTM standard, when you're testing for quality assurance of new shafts, they really want you to do 3 tests if it's greater than about 2.5 feet in diameter.
Okay.
I don't remember, I think the cutoff might be 30 inches in the standard. The idea there is, now, that's not going to be possible if it's under grade B, for instance.
Right.
You know, that for forensic investigations, that's not an issue. This is for if you're testing a new shaft for quality assurance acceptance. That's the ASTM standards designed for that. And the reason they do that is you can think of a worst case shaft situation. Where you have a large diameter, you know, like a 6-foot diameter shaft. And if you mounted your accelerometer here and you hit here and you have a partial defect here, your wave energy takes a little while to develop all the way across the shaft. Typically it's about 2 diameters based on the physics before it's really a true focused plane wave going down, covering the entire shaft. So in other words, at 12 feet, it'll pick up this defect just fine, but it'll miss this one. So if you also tested here and hit, that wave will echo here. So on a smaller diameter shaft, it doesn't matter. If your shaft is only this big,
Right.
yeah, it won't really matter. So that was the idea. Trying to, you know, they're trying to not miss shallow defects on really large diameter shafts.
Right.
But again, not really applicable to forensic investigations. I kind of like this picture. It's an interesting one. I asked people, what's wrong with this setup? Can you see what's wrong with that test setup?
Yeah, I think the geophone, it's on the metal plate.
Right. Ding, ding, ding.
Yeah.
Do not mount your accelerometer on a steel plate.
Right.
They almost never work. It might work in this case if that steel plate is embedded in the concrete and fully bonded and has concrete up underneath it with really good consolidation.
Right.
But that's really rare.
Right, that's...
Most of the time, something like this, that accelerometer will just go beep into the ring like that.
Okay.
And you might see a shaft bottom echo hidden in all that ringing, but it's so simple just to move it right to here.
Right.
Instead of here, or here instead of here. Yeah, so never mount on steel if you can help it.
Right.
Yeah, I mean, there's times there's no way around it. You can try it, and if it's really solid, it can work. But it has to have been embedded in the concrete at the time of placement. If it's bolted to the top of the concrete, it will never work.
Even if it's bolted with grout underneath?
Okay, if it's bolted with grout, it might work, but grout debonds really,
Right.
Over time. It's still unlikely. It's still not ideal. I have seen it, we've done it successfully in that type of situation where it's bedded, bonded, either with grout or embedded in the concrete, but it's just not ideal.
Okay.
But otherwise, this is this is kind of a typical cell phone tower, some kind of antenna tower test. The data analysis, of course, you're looking at reflections, getting the depth of the pile or defects. The impulse response, you can get dynamic stiffness, but we're not going to worry about that today. So this is your basic scenario. This is where we're talking about impedances. Free means that the ideal case would be a shaft where the end of it's just in air. Something that's less stiff than the concrete.
Right.
So most soils are less stiff than concrete. In which case you get an initial downward break and your bottom's a downward break, right? If the bottom is stiffer than concrete, which may be the case with your limestone, an infinite limestone, then instead of breaking down, it breaks up. It breaks the opposite direction.
Okay.
By the way, so if your laptop breaks up first, then it will break down. So it's opposite. It's not up, down, it's just same, different, opposite versus same.
Okay.
Yeah. So in other words, in your laptop, this could be up. One thing we might do in a future, actually, software update is to have a button to allow inversion of the data, but some people like it inverted from the way we do it.
Mm-hmm.
There's some manufacturers of other equipment that their normal is up, and our normal is down.
Okay.
It's just what you get used to. I'm really used to 30 years of looking at down.
Right.
And I have a hard time looking at upward breaks at initial, at data that's upward breaking, and I like to invert it before I look at it, just because it's easier for me to see. My brain is trained that way. But the new USB one that Dave we just have we're just starting to put together, it will take care of that issue. It'll always break down because it will be independent of the laptop.
And that's the one that eliminates the audio.
You're right. It eliminates the audio port. It's just purely USB based, and the data acquisition is now on the little module.
Okay.
And so it always has the same polarity, no matter what you do, because it's the same hardware every time.
Right.
If we wanted to change the polarity, we would change the wiring direction in the module.
Okay.
But we won't. So mobility, that's the IR analysis. We won't talk too much about that. So this is basic accelerometer data. This is your basic IR SE data from a real shaft. Now this one likely has a shallow bulb, probably a big pile cap or something. And that's what this giant upward break here is. But it's breaking down, kind of damps out. You get a nice echo about 17, 18 feet. The software allows you to average these peaks. So it's 17 feet, 17 feet, 17 feet, 17 feet. It's probably actually, 18 and 16 and,
Right.
depending on where exactly you pick it. If you can see multiple echoes, you normally can get more accurate data by picking 2 or 3 peaks, echoes. But it's not, you can even see it coming in again here. This little bump way out here, but it's, not much. And then impulse response shows similar, don't worry too much. So this is a kind of a nice little example where they embedded geophones in a shaft. So this shaft had this is very old slides, these are 25 years old. But this one had a geophone buried at 46 feet and another receiver at 86 feet. The bottom is at 92. So it shows the waveforms from these various channels that were all collected from the same hammer impact. And it's kind of nice. You see the initial hammer impact and the initial response of the receiver at the top. Then you see the response of the receiver halfway and the receiver at the bottom. And so you can see this wave going down the shaft and then back up the shaft. And then back down again through this second echo. You know, if we had a long enough record here, we would see another echo out over here from the bottom, the second bottom echo. So it's kind of nice to see how these waves, you know, they are trackable. You know,
Right.
You can see them going down the shaft and back up. You know, this middle one is kind of interesting. It shows a delay and then the first echo and the second echo. And then if you happen to have a geophone at the bottom, you can even calculate the velocity of the concrete. You know, it's just a direct arrival. So it's 86 feet over the middle section for 13,400 feet per second, that particular shaft. And we won't worry too much about mobility, but shaft bottom, I mean, you know, the equation that the software takes care of for you
Right.
is just simply velocity divided by time over 2, because it goes down and back. So it's feet per second divided by seconds gives you feet, and you divide by 2 to get the actual depth. Yeah, we won't worry too much about IR. So this is something we sent you. You should have a version of this.
Yes, it's about like
Yeah.
8-10
Yeah.
pages on. Yes.
And so I was going to go through some of the most important ones here, but these are the kind of things that you can run into in a shaft. This is what your shaft has, is basically a rock socket
Right.
situation. Now, the thing to keep in mind, a bottom bell and a rock socket will look very similar to each other. Yeah, because their impedance increases at the bottom. A short shaft and a break will look the same. You can't tell the difference between a broken shaft and a short shaft. But, you know, except that the owner says it's supposed to be 40 feet and it's
Right.
only 20.
Believe that there existed data. Yeah.
And it doesn't matter. It's going to act like a 20-foot shaft, whether it's broken or short.
Right.
It'll still be short. And then we have long bulbs and short bulbs, and inclusions and necks are the same. You know, an inclusion is just a neck that's inside the shaft instead of outside the shaft. Yeah. So this is your normal sound. You have the initial response. You see it echoes, it rings. It'll always ring a little, and then it damps out. Nothing much happening. Boom, boom.
But
Yeah.
it rings out on top of the 0 line, right?
Well, sometimes, or it can be at the 0 line or slightly below. That's not so critical. A lot of that has to do with somewhat with the impedance of the shaft. And if there's a pile cap on top, we'll change that as well significantly, because it can change the. I usually don't worry too much about where it is when it's flat. It'll be just above or just below, but it's not super critical. What matters is the change, the echo,
Okay.
you know, and how big that is. But,
Well, it's
yeah.
when you see a drastic change on the wave, that's
Right.
what you.
That's what you're looking
balance.
for.
Okay.
Right. So this would be a short shaft. Again, it's above the line. It has a little bit of ringing here, but then a big boom.
Right.
And so that's a short shaft. But it also could be a defective shaft, a fully broken shaft will also.
Right.
Typically, the only difference might be a fully broken shaft will often have an even bigger echo here and multiple echoes, because a broken shaft will have true air below it.